Thank you very much. Good morning, everybody. As was said, my name is Daniel Fischer. I'm Head of Application Robotics Data Systems at ESA, and it's my pleasure to moderate this panel on a very interesting topic, software-defined satellites and how the technology will be applied to future missions. Before diving into the topic, let me introduce my fellow panelists. You have met Xavier already, Head of Future Projects, working in the Telecommunication Integrated Applications Directorate at ESA. The next physical attendee here is Dave Evans, who is the head or the project manager for the OPSAT mission. Dave, if you would like to come to the stage. Okay, I see also our online panelists. Good morning. There is Mathieu Bailly, who is co-founder and head of space business at CYSECi. And we have Simon Reid, who is managing director of D-Orbiti. So,
good morning, Daniel.
With this, with the panelists all present physically and virtually, I mean, connecting, everything is connected, so also this panel. Let me give you a short introduction and then we can dive right into the question. So, software-defined satellites. It was said earlier that software-defined space is not a topic you can find on Wikipedia, but actually software-defined satellites are popping up there now. So there are more and more articles in the internet, more and more let's say conferences and R&D on this topic. And if you look a little bit back, 10 years ago, a bit more than 10 years ago, we saw the emergence of software-defined networks in our ground communication networks. So open flow protocol first, but then all the big companies also followed on. And now this is basically the state of the art. Everything is reconfigurable, all the routers, all the network nodes, all the physical devices, flexible, cheap, and basically the backbone of our modern life. So this happened a little bit more than 10 years ago also, talking about the 10-year innovation cycle in the business. And now we are at the point in time where we see this happening in space. We are seeing that we no longer fly spacecraft, or we plan to no longer fly spacecraft with very fixed and very rigid programmed hardware on board, but rather now we see that software is taking over the part, the onboard software, the firmware, and it can reprogram the satellite on while it's in operation, and thus opening also new business fields. We see small startups, new space, eagerly jumping into this topic because they can basically rent the spacecraft, reconfigure it to provide the service to their customers, and then hand it back to the operator, maybe later on. So this is kind of really satellite as a service kind of thing is really connected to that. But of course, with all this flexibility, reprogrammability, and freedom comes also the increased risk of cybersecurity, which is also a big topic today at the conference. I mean, if you think about it, you could say that maybe at some point, even if there is a vulnerability discovered somewhere in a terrestrial network, it immediately will apply also to the space network at some point. Yeah. So we have to be able to react really quickly and fast to these kind of things. You could even think of the extreme example that you have these kind of fancy hacker tools that autonomously browse the internet for vulnerable systems and give you entry doors to businesses, that these kind of AI-driven security vulnerability searches will also apply to space. So this would be an extreme example, but we can see maybe this happening. So there's a lot of things happening, and I'm happy to talk with my panelists about this today. I have two sets of fixed questions, and then maybe we open it up to the audience, so you can already think about interesting questions you would like to ask. So the first question goes to all the panelists, and it's basically the basic one. So how do you see software-defined satellites impacting your business, and in particular future missions in your business? And why don't we start with Dave?
Oh, thank you. Thank you very much. Thank you for the opportunity to talk at the conference. Yeah, it's an interesting question, but I'm not an expert in everything. I look at it through the lens of my area of expertise, which is the OPSAT Space Lab. And I'd like to answer the question with a couple of stories about OPSAT-1, which I think highlight the idea. So just those that don't know, OPSAT is a flying configurable lab in space. The idea is that we give this to third-party experimenters. We can configure everything. We have a reconfigurable FPGA in space and the software. We don't test it very much. We have no contract with the experimenters. They just uplink their software or firmware. It's tested, and we look after the security or how can we say the risks associated with that on our side. It's therefore allowing industry to really innovate very fast and fail fast, etc. Now, one of the implications of that is, of course, that you have to design the spacecraft very good to be, if you're just going to let people loose on your spacecraft, this is something you just don't do normally. And I gave the design team an idea to design against, and I said, like, you have to have the idea of an evil experimenter. Yeah, so an experimenter that's going to do evil things on the spacecraft, and we have to be able to deal with this. And just by luck, the idea of an evil experimenter is very similar to a hacker. Yeah, so even though we didn't launch OPSAT-1 with the idea of doing cybersecurity experiments, later on when we actually launched it, it came as like, it's almost there, as an idea. Now, what's my story? So the first story is that when we launched the spacecraft, it's a low-cost mission. We realized that on the onboard bus was going to be a bottleneck. And although the rest of the system could do quite a lot of downlink, the onboard system was going to throttle it significantly. And we didn't have time to do anything about it. So we decided, okay, we have a reconfigurable spacecraft, let's just put a wire in. So we made the hardware connections that were necessary, but none of the firmware or the software to actually implement anything. We didn't have time to test that. We just put a wire in, tested the hardware connection was okay, and launched the spacecraft. And we said afterwards, when we're in flight, we'll do the rest. And this is what we did actually. So we actually implemented something called SpaceWire, which is a space-based protocol in space. I think we're the first people in the world to actually do this in orbit, and it worked. So we actually implemented this, and we increased our throughput by 6. What's interesting is that wasn't the end of the story. I mean, we just got more data, but actually, it didn't really impact anything except we were getting more data down. What happened then is an experimenter came along and he said, "Oh, now you've done that. Now we've got a bigger something called MTUs, transmission units. We can implement IP in space." And we said, "Go ahead, do it." And the guy implemented IP, a TCP/IP, in the end. And suddenly the world changed because we were flying onboard Linux, and once we got IP, most Linux applications have a native IP interface. Suddenly, the world opened up. We increased the efficiency of the mission by an order of magnitude, because things that we were trying to develop on ground, doing the traditional way and then testing them and launching them, etc., suddenly were one-liners. We were just looking on the internet for software, installing the packages, and implementing them in a day. And it was a completely different thing. So this is one aspect. The other aspect is that at the same time, I got called by Mathieu here, who's going to talk later, as an OPSAT experimenter, and said, "Hey, we'd like to use your spacecraft for cybersecurity exercises." And it seems to be perfect for this sort of activity. And I naively thought, "Oh yes, of course. Why not? We'll just do this." It turned out to be much more complicated. So one of the lessons is that if you ask your team, "Is the system secure?" you will get one answer. If you ask them, "We want to test this with some white hat hackers to try and penetrate the system," you'll get a different answer. And this is a fundamental reason why you have to do it for real, because that's our experience. The second thing is that the passions that were raised because we were trying to do this within ESA were very, very high. Yeah, lots and lots of discussions, etc. We released the demon in everybody, and then there were lots of shouting, etc. In the end, we were ready. We did the technical thing. We were ready to do this. And then the war broke out with Ukraine. And in the end, we were prevented from doing it for the moment. However, the moral to the story is the one thing, when we're doing the risk analysis, the one problem we had was the same problem of giving us all the advantages. It's the same thing. It was the IP connection. Once we have the IP connection, which was giving us all these benefits, it was also the very same thing which was exposing us to lots of vulnerability. And that's the message I want to get across. It's the same thing. The challenge and the opportunities, they're identical. Thank you.
Oh, thank you, Dave. So I think it's the perfect time for Mathieu to take over and continue.
Thank you, Daniel. Thank you, Dave. I loved your anecdote, Dave. Let me bounce back and maybe take a step back for a sec. So we're talking about future missions, software-defined. I think software-defined missions are the future, but it's just a way to enable a new business to have more commercial opportunities. So software-defined missions will enable more processing on board. Just like we do edge computing on Earth today, we'll be able to do more processing, more computing on board to process data and to add more value to the mission. And also, the goal is also to enable new business models. We see it in the cloud on Earth. Having a shared infrastructure can reduce costs, is very appealing, is very attractive for customers, for users that need these data in space. And these are already trends that are embraced by companies like D-Orbit. Simon will talk about it. Loft Orbital. A lot of companies have understood that this is the future. As a service missions, AI, ML on board to reduce the amount of data that are downlinked. This is what we're heading to. And these have a lot of benefits, but also a lot of drawbacks in terms of security, in terms of challenges. And as Dave said, it's really the two sides of the coin. So you have lots of benefits, but on the other side, you open up a whole bunch of different attacks. So the attack surface increases. And then this is where you need to look at security mechanisms. And this is new to the commercial space sector. And this is really the challenge for the future missions. The challenge because today engineers are not trained in security. If you graduate from Super-Héros in France or TU Delft from space program, you don't study security, you don't study crypto. This is the first obstacle. And also, there are no products today available on the market. If you want to launch a new mission, software-defined, very modern, small sats, constellations, there are no products out there that you can buy off the shelf to secure your data, to secure your software. And this is the gap we identified at CYSEC, and this is what we want to fill. So this is the challenge I see today, and so part of the vision of Europe. We see the constellation European Secure Connectivity. This will be a dual-use missions. We know that there will be government and also commercial users using this infrastructure. So these are the challenges we're facing. And these are the threats. And now let's talk about the solution. And ethical hacking, as you mentioned, Dave, I think is absolutely instrumental in the way of securing these future missions.
Thank you, Mathieu. Xavier, you want to go next?
Yeah, thanks. Thank you very much, Daniel. So I look at it and I explained a lot about 6G. So I'm a true believer into the software-defined everything, and applying naivety, and then you guys, this community will find the solution to the challenges of security, etc. So more in general, in the field of telecommunications via satellite, there is a key trend into software-defined. We call it payloads, not just the complete satellite. For me, a telecommunication satellite is basically a platform, a service module, and then ideally a software-defined payload. And this is a direction of flight, very clear. And I always use the example that 20 years ago, the dominant service in telecommunication via satellite was television broadcast. And there, we basically, it was a fixed kind of, transmission. The content was changing, but the way of conveying that content was fixed. And the trend was into bigger and bigger satellites. but it was not changing that much. However, a satellite in geostationary orbit has a lifetime of 15 years. And in 15 years, we saw the change from analog television to the first digital television to new standards. So when you have an architecture that is fully transparent, you don't care. I mean, basically, it's an antenna, a receiver, down converter, and then you do a conversion, amplification, and another antenna, transmission to ground. But the interest is more and more when you do processing on board the satellite. And there is where changing from one standard to the next in terms of digital transmission can make your ASICs completely irrelevant or your satellite completely inefficient. And there is where I think there is a must. We are going in the direction of having more and more software-defined payloads. And in that respect, for me, an ideal software-defined payload is the one that just has antennas, the minimum amplification, frequency conversion is needed, and then you do conversion into digital, and everything is digital signal processing. And there is where, when we combine with the phenomenon of miniaturization of electronics, we see more and more possibilities in terms of the processing power on board, be that with general purpose processors, digital signal processors, or specialized processors of any kind, together with all the memory that is necessary. So, for me, this is a clear trend that we see, and not just for the experimentation, as I mentioned with 6G, but also for the say commercial type of missions, so that the flexibility that is necessary to adapt to future evolutions is provided. And then we are counting on, as I said, on this community to make it secure. I mean, ideally, I always follow with high respect what Dave started with OPSAT. I mean, ideally, having this Linux on board and being able to upload packages and configure the computer, for me, I mean, is the paramount of the ultimate solution for the software-defined payloads. I leave it there because I talked a lot earlier.
We will have other questions.
Thank you.
So, Simon, from the perspective of a commercial space service provider, how do you see this?
Thank you, everyone. Thanks for the introductions and the great speeches earlier to try and set the scene. So as you mentioned, D-Orbit is a commercial, privately owned company. Doing our focus is space logistics. I mean, what we're known best for now is orbital transportation. So we have an orbital transfer vehicle, and its purpose is to deliver CubeSats for constellation customers into their right orbital slots. So we've got customers like Planet, Kleos, and also Astrocast, who are building a satellite IoT network with CubeSats. We've successfully completed 6 of those missions so far, and this is now turning into a regular service. The next 2 are going up in December. On these missions, we're also getting involved in a lot of testing of new technologies for example, inter-satellite links, optical communications. And so that's the logistics story in terms of physical logistics. But the second thing that we're working on now is really the what I'm calling the data logistics. So all of our customers are really there in space in the first place for collecting data, right, or moving data around. It's a data business. And what we've observed is that our opportunity that D-Orbit has from our regular launches is to actually take compute into space with us and actually provide a computing service on our spacecraft, which is more in the frame of data centers, not quite sort of going beyond the edge processing that you might find on some CubeSats, to really put some meaty compute capability in orbit that's enabled and sort of supports all of these new connectivity options in space, which allows networks of satellites to be interoperable, communicating with each other, and and operating in a coordinated sense. So we've already put testing this capability on 2 of our spacecraft already. One is with a hyperspectral sensor, also on the same spacecraft that ESA have supported. And so this is there now as a demonstration and test platform. So we're learning how best to use this capability. Now, in terms of usability, we're deploying it as a cloud, right? So cloud computing in space. So what the cloud enables is really, it becomes accessible beyond sort of embedded software engineers, which is the traditional way of putting software onto satellites. It's going beyond even typical, normal software engineers, if you like, cloud software engineers. We want to put a capability in the hands of data scientists, people who are actually able to make use of that data and exploit it. And why do you put it in space? Well, this allows things like almost near real-time processing. So Earth observation systems like Sentinel, it takes 4 hours for the data to get to users. But we've been able to show things like, detecting floods within a few minutes, which of course, once you've got a flood and you can detect that using AI on board, you can then, very small message, you can, enact some response to that within, very, very quickly, or even cross task between other satellites to zoom in and look for more information like that.
Thank you, Simon. So we heard a lot about small satellites, CubeSats, probably because they're the most graspable experimentation platforms, the cheaper ones that you can have. But maybe, Xavier, you can tell us a little bit more about the plans for software-defined satellites in the big missions, like commercial missions, but also especially institutional missions.
Yeah, so I think software-defined is not valid for everything. So, as I said, in the past, it was very clear, no? Transparent satellites, or be that for a television broadcast or for fixed communications, were fixed in terms of architecture. And there are missions that require things to be stable for a long time. And there are, unique capabilities for which, you want to protect that and to keep it stable during the lifetime. I'm talking about, very expensive institutional missions, or in areas where, you just can do with a data relay type of function without any processing on board. We have, for instance, EDRS is the European Data Relay Satellite System. Basically, its function is to collect data from Earth observation satellites using optical comms, and then relaying that data to ground or to other satellites. For that, you don't need to do any processing on board, and therefore, there would be no need for software. If I think about, a future project that we have in that respect, that is an optical fiber in the sky called Hydron. Again, there would not be any point of transmitting a terabit per second and then do any kind of processing on board. For those, you just transmit optically or process the information optically without any need for software. However, I think that the software-defined is not just for the small missions. It is easier to test things. It's easier to get through, any kind of, say, ethical hacking and so on. The system secure, and I think there will be the moment that the technology of software-defined payloads will be ripe for more institutional and commercial missions. And we have an example with the European Secure Connectivity Initiative of the European Union. Obviously security is paramount, and there will be aspects that will be rather critical. But there are a different grade of services, and I think even in there will be room for some software-defined payloads that can be programmed and adapted in the future.
Okay, thank you very much. So we will not see anytime soon a software-defined spacecraft at Jupiter. Probably not. For the next,
no, yeah, indeed. I mean,
decade,
yeah. For those, very unique one-off kind of missions. Definitely, I think you want everything to be fixed as much as possible. Indeed.
Okay, so maybe now we heard also a lot about cybersecurity before, and Dave, you brought up the topic earlier. It was very interesting. Your experience with OPSAT-1 and cybersecurity hacking event. Can you tell us a little bit more about the lessons learned from that experience and how you probably will continue this, or how you would make it different in a follow-up mission like OPSAT-2, for example?
Yeah, sure. I would say that I have to thank CYSEC and Mathieu. I say that again for pushing ESA to actually do this. At least we got to the preparation stage, because there's a massive difference between just talking about things theoretically and actually doing things. That's what I found. And when we actually started to do it, one of the things that came up is the idea of the evil experimenter was okay, but it wouldn't stand the test against a serious hacker. Yeah, so we got to find, by doing proper analysis and following the standards, etc., and talking to the experts, we found many ways in which a serious hacker could actually get into the spacecraft. And and this led to lots of lessons learned for if we need to do it again, then there is things we have to change on the spacecraft, because you can always reconfigure the ground. But there's a certain amount of reconfigurability that isn't possible on the spacecraft. Or even OPSAT, I say it's completely reconfigurable. Well, there is a limit. There is a limit to it. Of course, there is a safety limit, and we reached those. So for OPSAT-2 or OPSAT Volt, which I'll talk about in a minute, then definitely we will take that on board, so that we have that ready to do this if the need arises in the future. We get experimenters that are interested. For the next generation. Another thing I would say is perhaps the HackerSat type idea that we had, maybe this was a little bit too brash. I don't know. It's certainly, like I say, there was a lot of passion generated. People shouting at me on the phone saying this is not a playground, for example. And you have to take that into account, because they have a valid point as well. You have to have, it has to be for everybody. So we have to sort of think about what's the best way to do it in the future, what's the best format. There's a need, there's definitely a need, and prepare for that for OPSAT-2. So OPSAT-2 and OPSAT Volt, they're in progress at the moment. I'd like to also thank TIA, because these are TIA programs run under Skylight, which is the optical and communication special program line that Xavier talked about earlier. And we're supporting TIA for those missions. But what's important there is optical and quantum, because that's the main point. So the main point of the mission. And whenever you start talking about optical, you start thinking security. I mean, this is what's come up. And I would love to do tests, real tests, with an optical quantum-enabled satellite to check out, just the same way as we did with OPSAT-1, but let's see if it's really secure. Let's see if it can't be hacked. Let's see if the theory that's been talked about is really as good as people say, because my experience is you have to do it. So that's my take for the next generation.
Very practical approach to things there.
Yeah.
So Mathieu, I mean, you heard Dave talking. For a company like CYSEC, focusing very much on cybersecurity services, what could you tell us about your perspective on future business related to cybersecurity in satellites, and especially software-defined satellites? Do you see this as an expanding field, and how would you what's your strategy?
Maybe before I go on the strategy at CYSEC, just to bounce back from Dave's comments, and again, I'd like also to thank Dave for his support. He was very open to the idea of using OPSAT for security experiments, which it turned out to be, let's say, tricky to do. We didn't do it in the end because of the war, but at least we did the exercise properly to really show that there are some benefits to allow ethical hackers to identify vulnerabilities in a space system. And this resistance that we faced with Dave, we also face it at CYSEC on a day-to-day basis when we talk to new space operators trying to pitch our security products, because they don't really understand the risk, the cyber risks. And this is really the perception of the risks that is critical. If you have no idea that there are some bad guys out there, they take down your service, you don't want to add a security product to your satellite. You just see it as another risk in terms of reliability. Why would I add software for security if I don't know who would be interested or who would be willing to attack me? So it's really about education, and that was the whole purpose of this Hack SciSat challenge. It's to show that hacking a satellite may not be as hard as you think. And as a space engineer, if you've been following ECSS standards, if you've been following really guidelines, standards very closely, very thoroughly your entire career, it's hard for you to understand. There are some guys that are very, differently brained, that can look at the system in a very different way. And these are hackers. And this is how they think. They think differently to find the open door, to find the weakest link of the system. And this is what we're not used to do in the space industry. And this is what we need to change to be more secure. That's the purpose. That's the bottom line, to be more secure. We want these people to help us find the holes, find the vulnerabilities, to make it more secure. This is what we try. That's the message we try to convey with Dave to ESA and also to the world, to Europe, space industry in Europe. The US have understood that a long time ago. That's why they're doing Hackasat. The US Air Force is pounding millions of dollars into these Hackasat experiments. They are recording every single move, every single message of the hackers during the competition. These are very valuable data for them to understand how these hackers think, how they find the holes, how different they look at the system, and in turns they will use this data to secure their own systems. So this is very smart from the US Air Force. They do it with a very clear purpose, and we need to do it. We must do it also in Europe, and that's why Hack SciSat was a precursor. And OPSAT-1 was and still is the perfect satellite to do these kind of experiments. I've been looking around. I've been asking a lot of people last year to find other spacecraft, but OPSAT was designed perfectly to do these kinds of demonstrations. So it's. I think this is something we need to do in the future. And maybe to finish, as I said, like with the two sides of the coin, we have more software-defined missions, more processing. We fly Linux. This have a lot of benefits, but also you increase the attack surface. And Dave, if you remember when we talked to the hackers, they told us when they looked at the documentation, they looked at the spacecraft, they said, well, it's too easy. Like they could find vulnerabilities. There was no technical challenge for them. They said, like, even if I do this, I cannot publish because it's not. I will not find a recognition, technically speaking, to do this. It's not very challenging from a technical standpoint. So that shows also that there's really the need for that to increase the maturity of the industry about security practices. And maybe I did. Sorry, Daniel, I didn't answer your question. Maybe I can do it on the next round. I was already.
That's okay. So thank you, Simon. As a commercial operator, of course, your prime concern is to deliver your service, to bring the spacecraft of others in their orbit or de-orbit other spacecraft. So for you, the security is probably something that you need to think about, but it's not really your primary business function. So how do you approach this? Are you tackling this yourself? Are you making use of companies like CYSEC or others? So what's your take on this?
Thank you, Daniel. Yes, and I'll just pick up from something Mathieu said just then around, I mean, many years ago, I was a software developer and I sort of had a revelation one day working on a spacecraft commanding system, and suddenly.
Okay, maybe you can just stand up and then ask your question.
Yeah, shout.
Oh, we have.
Yes, yeah, so they're back.
Yeah, thanks. So I also believe that we in the space sector are lagging a bit behind in security, especially when compared for what we're actually doing in everyday life on ground here. So what's helped the ground-based industry, for example, the IT sector, very much is the concept of post-mortems, of after incidents. Is there something similar planned, for example, the OPSATs work done during the CYSEC conference, or more in general also on ESA as a public entity, which might have an easier time to opening up in that regard? Is there any plans on that?
Guess that's more for you, Dave.
Yeah, that's a really interesting question. So the answer is, of course, that the ESA has its own lessons learned process, and we have recorded the changes we found, etc. But you always have to be very careful with security. So again, we'll come back to the same thing of is it wise to release this to a wider public, of which holes we had, and this wouldn't be my decision to make, as whether we do a hacker site isn't my decision in the end. You know, I only make recommendations, but I think it's a really good question. I shall take that with me, and I'll ask the question at least, even if I can't answer. Well, thank you.
There we have another question over there.
Hi, Baldur from Cybernetica. Where would you put in the pen testing in the current satellite design process? Because yes, I know in Europe we certify a lot, but pen testing is probably not yet state of the art of satellite design.
You want?
Yeah, are you talking about the OPSAT experiment, or are you talking generally?
Generally, satellite design process, where would you put pen testing as a standard step?
Okay, so I can only talk about, so pen testing is done. So it's something I also found out from the, on the ground level. For the satellite experiment, what we did was say you get a direct IP connection to the spacecraft. This was the limits that we said. You go up there, and then once you're in to the satellite, because this is what we give to experimenters. So experimenters get an IP connection from their bedroom directly to the satellite. This is what we offer as the satellite flies over Darmstadt in Germany. And then from there, they had to break out of that, because of course they're in their own area with certain privileges. They had to break out of that and start causing havoc. So this is how we did it. Now, of course, that wasn't what was concerning the ground people. What the ground people were saying is, yes, but how do you ensure that they don't break out at some other place? And there are multiple firewalls to go through, etc., places where servers could be brought down, etc. And from there, they could get into other areas, which are operational missions, etc. So yeah, this is where we learned a lot. I mean, also one of the things I learned was it struck me as really obvious, but you could also, once you're on the satellite, you can also go backwards into the network. So you can use the satellite as a base on which to cause havoc going the other way, and your firewalls aren't necessarily set up to think about an attack coming from that direction. So all this had to be taken into account, which was completely new to me, and to quite a few people, and we learned that as we went along. Okay.
Thank you. So I see now that our two online panelists are back. Yeah. Probably it was a cyber attack. We don't know. But I leave Simon to finish his speech.
How far did I get? I wasn't sure how far I'd got. What I was explaining is really how we're trying to put the context of our security, alongside the rest of the functionality that we're reusing from the cloud environment. So working with the hyperscalers, which are businesses in their own right, who are some of the biggest businesses in the world delivering cloud-based services, on which our business depend. We're using some of these companies for our own terrestrial business. We have to make a decision about the security of that before even thinking about the spacecraft. And so we're trying to model our cloud-based space service based on, a terrestrial cloud-based service in every way in terms of the functionality, usability, and security. And those services themselves have a kind of a job zero, which is to make their services secure. If AWS or Azure wasn't secure, their business would be gone overnight. But then that's sufficient for commercial users. But within that, if you delve into those services, you find that there's a lot of providers who are offering value-added extra security layers for particular types of function, for protecting containers in a particular way, or protecting types of applications, or encryption of services, or quantum key management, and there's all sorts of things like that, which are provided as layers within the marketplace, within the basic cloud service. So that's the kind of approach that we're taking to this. And companies like CYSEC, who we are working with already, fit into that mold. And of course, the knowledge of those, the particular context of space and how the spacecraft will be used by users, that's the kind of thing that Mathieu, I know, has been looking at, and his team really closely. So we've been doing a test on one of our satellites with our hardware, hardened operating system, which is protected by all their software, really great testing and learning. And, David has mentioned learning, finding out things as well. And that's very much the journey that we're on as well. By, putting this stuff into space, we can sort of demonstrate what we think we know, but we also learn a great deal as well about the sort of the unknowns, and practical things that you might not have foreseen already.
Okay, thank you, Simon. So it's 2 minutes left, probably not enough time for another question. I don't know. Can we have another question? Yes. So any more questions in the audience? Do we have questions online, maybe? I don't see anything on the screen.
Good morning. Thank you. Very enlightening set of comments from the panel, as well as our virtual panelists who've come back from the hack the sat, whatever happened there in the connection on the downstream communications. The topic of hacking a satellite in cybersecurity, I heard the comment that the hackers found it to be too easy. Are we talking primarily commercial assets? I know in the U.S., the defense and high orbit sats rely heavily on the National Reconnaissance Office and other governmental entities, and they rely heavily on encryption to secure the comms and the data that's gathered by the satellites, and then obviously communicate to U.S. and partner-based intelligence and military assets. So is that where the ease is? Is that really where their focus is? It's commercial, right? Not which is obviously used by defense and government as well as to expand capability, right? As we saw in the Viasat Ukraine kind of thing, and how SpaceX has become instrumental. So just to summarize, the ease of hacking is more. We're looking at the commercial sector. Is that correct?
I think it's good you brought it up. You shouldn't use the OPSAT case as generalize it to space, either commercial or institutional. So it's a special satellite. It's designed for new things. It's running COTS software, etc. So, but we were surprised that how easy it was. But that shouldn't be generalized to other missions.
Okay. So it's sort of an exploratory discovery of what the art of the possible is without it being an exemplar.
It comes back to the comment I made earlier that there's no other ESA satellite running Linux with an IP connection. Yeah, so maybe in the future we will have them, and New Space are definitely using this. So we're protected, if you like, for the old satellites by maybe because it's bespoke. It's there's a lot of effort you need to put into, and as Daniel said. But the moment you become terrestrial, you get all the advantages, but you get the disadvantages. There are tooling there on the internet you could download, after in lunchtime. Yeah, and this would work against such a satellite.
You would agree that the foundations of cybersecurity in space starts on the ground, that from your manufacturing, your supply chain, your software bill of materials, your firmware, that if you take care of as much of what you can do on the ground, the issues in space then become a little bit different, sort of, atmospherics, satellites that explode, near constellations, as we saw as well, or satellites with probing arms, or electromagnetic, warfare to interfere with satellites. Would you agree with that statement? Is that conceptually kind of?
I don't think there's any difference really, because it's a server. It's whether it's flying in space or flying on the ground. There's slight differences there with the communications like you come up, but in the end it depends on what you're running, how is it connected, and what security you put in place, just like if it's in a data center.
Yeah, thank you very much.
Okay.
So thank you very much. I think it was a very interesting discussion. Thank you to all the panelists, and thank you for the audience. Enjoy the rest of the conference.
So let's wrap up with a